Hello, this is part 2 of lecture 1B in the series of lecture for Chemical Engineering Thermodynamics. And just a recap for part 1, we talk about first law, the first law of thermodynamics, and we apply the first law into closed system and isolated system. Okay, the essence of the first law is basically one sentence that energy is conserved. And for this lecture, we are going to take a detour to clarify one more variable, work. Okay, so the work in this case, if you recall what I mentioned in lecture 1A, there are two kinds of work: mechanical work and non-mechanical work. So by the name itself, it is very clear. For non-mechanical work, it is everything else except mechanical. Okay, the very good example of non-mechanical work would be electricity. If we focus on mechanical work, we can divide them into two groups. The first one is called expansion work. Basically, it is about expansion of system volume. For instance, if I have a piston cylinder assembly, like in this picture, if I expand somehow, if I, let's say, heat up the gas inside, the system would expand. This kind of thing would cause us work, and this work is called expansion work. Okay, so if you put this piston cylinder assembly underneath your car, you can lift up your car simply from this expansion work. Another kind of mechanical work is called non-expansion work. So by the name, it said it has nothing to do with the volume of the system. So in case of non-expansion work, the total volume of the system remains constant, but you can apply work in there. The good example of non-expansion work is shaft work, the work of rotation of the shaft, like in this picture. You stir whatever inside. In order to stir it, you need to give up some energy to the shaft, and such rotation basically give the system some energy through what we call work, and this work in particular is called non-expansion work. Okay, we are going to focus on expansion work at this moment. Alright, so if I have a piston cylinder assembly and I push the piston down, so basically I compress the gas inside. In order to push it down, we need to give the system work. Okay, mechanically, the system receives force by the push, right? The force causes the compression of the system, and the distance of the piston traveling in the direction of the force in this picture is dl here. And note that the dl here goes along the direction of the force. Okay, if you look in the perspective of the force, dl would go in the direction of the force. But if you look in the perspective of the system, dl is going into the system. Okay, from physics, work can be calculated based on force multiplied by the distance in the direction of the force. Force is F, the distance is dl. Okay, but in this case, if you recall, the work, we put the notation that any work given to the system is supposed to have positive sign. So in this picture, we give the system work, so this work is supposed to be positive. However, if you look at the system itself, system is somehow compressed. The piston is moved inward. Okay, so with respect to the system, dl here has negative sign because it moves inward into the system. So dl is negative, force is positive. So therefore, in order to get work to be positive as the notation stated, we need to put negative here just to make sure that both sides share the same sign. Okay. Now if I multiply and divide by the area, cross-section area of this piston, okay, the area is constant. We can put it inside the differentiation or outside differentiation, doesn't matter. The force divided by area would give you pressure, while the distance in L direction here multiplied by the cross-section area here should give you volume. Okay. So the force is applied externally from the system. So this pressure is the pressure here. We call this one external pressure. Please remember this. By this definition, the pressure is supposed to be external pressure. Okay? And dV here is the change in volume before and after compression. In this case, for the compression, dV would be the change in volume, the volume after the compression, and with respect to the volume before the compression. If you compare these two volumes, the change would be this much volume, right? In this case, dV would be negative because the volume is smaller after compression. This negative and this negative would make the work to be positive as we like. Now, the del here, earlier we said del means small work, small amount of work, and d here means small change. So if the work is not small, the change in volume will not be small anymore, right? So if I change from small work to regular work, the change in volume would be integration of a small volume. So basically you integrate this equation in order to get net of the work. Okay, you integrate it from initial state to final state. Alright, please keep in mind right now we integrate it with respect to volume. So 1 here is supposed to be initial volume and 2 here would be the final volume. Okay, now if I plot from the equation, if you look at the form of the equation, work can be obtained from the integration of this form. And graphically, this integration means the area underneath the function. If you plot between Px, P of the external pressure, with respect to V, like so, then any form of function that we draw, we can calculate work easily by integrating the area underneath that function, right? So keep that in mind. So that's why we would put the graph here to have volume of the system as the horizontal axis and external pressure as the vertical axis. Okay, please keep in mind this is external pressure. It's the pressure outside, not the pressure inside. Okay, now if I have the piston cylinder assembly, and then inside here, let's say we have gas with the volume V1 and the pressure P1. Okay, it doesn't matter whether P1 will be inside here or outside here because right now the piston is at equilibrium. So therefore the force up here and down here are equal and the pressure would be equal too, right? So let's say that the starting pressure is P1. P1 would be atmospheric pressure. And P of the system inside here is supposed to be equal to P1 too, right? Now if I put a mass, let's say 100 kilogram of mass, before putting the mass on top of this piston, the pressure outside here is still P1. So the state of the system or the state of whatever we are considering right now is at this point. As soon as you put the mass on top of this piston. Okay, let's say that this piston is not smooth. Let's say there's some friction within this piston. So when you put the mass on top of it, it doesn't move right away. Okay, but at the moment that the mass is put on top of this piston, the external pressure on top of this piston is abruptly increased. Okay, so it's increased right away to another value, P2, and this P2 can be calculated from external pressure or atmospheric pressure and added with the pressure from this mass, right? Again, this is external pressure. It's the plot of external pressure. So whenever you put the mass on top of it, external pressure shoot up. But since the piston has not moved yet, so therefore the total volume of the system remains unchanged. So the function goes up directly. Okay, V1 here and V1 there remains the same. Now, if you leave the system for a while, I said that the piston has friction. It doesn't mean that it will stay forever. So if you put the mass on top of it, the pressure outside will be greater than the pressure inside, so eventually the piston would move down. Okay, when along the way, when the piston is moving downward, the total volume of the white area decreases. So the function should go from the right to the left, but the external pressure on top of this piston remains the same as P2. So my plot here is supposed to be horizontal line. So keep in mind, again, may I remind you that this function is not pressure inside the piston. This function is plot with respect to external pressure. Okay? From this plot, with respect to this equation, you see that the area highlighted as yellow area here corresponds to work. Okay? And this work is the work that we got from the compression of this system. So we call this one compression work. Okay? So you can calculate the area for the work easily, relatively easily. Now, at the end of the path, at this point, the pressure of the system should equal to pressure outside. So now pressure inside here is P2. Okay? So here at this point, pressure inside and outside are the same of P1. Here, pressure inside and outside are also the same but equal to P2. Here, they're not the same. Okay? So this point, maybe you can imagine this one as a transition point where the pressure inside the system and the pressure outside the system are not the same. Now, if I remove the mass from the piston, okay, as soon as I lift up this mass, the pressure on top of this piston would decrease back to P1 abruptly. So the function should go down abruptly along this blue line. Okay, right now at this point, external pressure returns to P1. But since the piston has friction, it doesn't move right away. So the volume of the system remains at V2 at this point. But eventually it starts moving upward because inside pressure is higher than outside. It moves upward until the pressure in and out of the system are the same. Okay? During the movement here, you have expansion of the system, so therefore volume of the system expands to the right hand side while the external pressure remains the same as P1. This blue line again is a function of P as a function of volume. Okay, external pressure as a function of system volume. If you integrate this function, basically you will find the area underneath the blue line to be the work. And this work is caused by the expansion of this piston. So it is called expansion work. Okay? From this picture, you will see that the compression work and expansion work are not the same, even though we analyze them from the same equipment. So going inward and going outward does not give you the same work. Also keep in mind that expansion work is the work that we can use. Okay? Again, if you put this piston underneath your car to fix the flat tire, the expansion work would lift your car up. That's the work you want. That's the work that the human want. But in order to expand the piston, you need to compress it first. Okay? You compress it first and then you expand it later. However, you should see that the work that you need to push the piston down to compress it is higher than the work that you obtain from the expansion. So it seems like this is somehow not good for human. We need to put work. We expect the same work in return, but we did not get the same work. We get less work. Okay? So as I stated, the expansion work in this case would be smaller than compression work. Okay? And it seems to be like this statement always. What we want is expansion work, and what we have to give is compression work. What we want is always less than what we can give. Alright? Now if I keep this picture in mind on the right hand side of this screen, I put a dotted line just to show you what it has been. And then starting with the same system, but this time I divide the mass into two pieces, 50 kilogram each. Okay? Initial state remains the same. The volume of V1 inside here, before putting mass on, the pressure is P1 here, and outside pressure P1 are the same at atmospheric pressure. But this time if we put one mass at a time, one piece at a time, so 50 kilogram first, you put 50 kilogram in there. As soon as it touches the pistons, the external pressure jumps up. Okay, it jumps up to this value. Of course, it does not go to P2 because the mass is only half. So the increase in pressure is increased only for half of this pressure. Alright? And then you leave the piston for a while, it starts moving downward. When it moves down, the external pressure applied on the piston remains the same because the mass is there. Only the total volume of the system decreases along this line. Okay? Once it reaches equilibrium, then you can put another mass on top of it. As soon as the mass touches the pistons, the external pressure shoots up to this value P2. And if you leave for a while, the volume decreases to V2. Okay? Now you can see that the red line from this picture, comparing to the red line that we derived earlier, we compress them from the same initial state and to the same final state. But the way we compress it are different. Alright? If you integrate this red line, basically you find the area underneath this red line. You get the compression work from the area underneath. And you can see that compression work in this case is smaller comparing to what we got earlier from putting one mass of 100 kilogram, only one mass at a time. Okay? One mass 100 kilogram right away. That means work depends on the path, right? So initial point, final points are the same. Only the paths are different. So this example clearly shows you that work is path properties. Okay, so same initial, same final state, different work, different area. So it's showing that work is path properties. Okay. Now if I lift 50 kilogram up, the pressure would be decreased to this point abruptly, and then the piston would start moving up because the pressure inside at this point is higher than the pressure outside. It will start moving up. Once it reaches equilibrium, you can lift another mass, another piece, and then it start moving again. Okay, you end up with this point, and the area underneath would be the expansion work. So if you compare expansion work in this case, when you have two pieces of mass, it seems to be larger than the expansion work with single mass, right? So it's also a good example that the work is path properties. Okay, and you can see that when you do it in two steps, the expansion work, which is what we want, seems to be greater than when you put only one piece of mass abruptly at a time. Okay, so you can predict, you can see the trend that if you divide 100 kilograms into two pieces, then the expansion work seems to be greater, the compression work seems to be smaller. So if you divide them into 10 pieces, you would expect the expansion work will be greater than this, and the compression work will be smaller than that, right? So basically, when you gradually apply load, the term gradually means when you put one piece, small piece of the mass outside, or you put the small load at a time, and before you put another load, you have to wait until the system reaches equilibrium first. Okay, by doing that, you slowly adding the load. In doing so, the compression work that is required would be less and less. On the other hand, the expansion work that you can expect would be more and more, right? So from this, when will they be equal? Can expansion work and compression work be equal? Okay, theoretically, it seems to be possible. So if you look at the step here, one step means you put one mass on top of it, right? So if you, let's say, divide this 100 kilogram mass into 1,000 or 10,000 pieces, okay, imagine you put sand on top of this piston, one grain at a time. When you put one grain of sand in there, you wait until the system reaches equilibrium, and then you can put another grain. You keep doing that. The process would take so slow, but the work would be, expansion work would be much higher than putting two pieces, right? So when you draw the function, you get, seems to be curved line like this. But if you zoom in, it still be step, a small step. But the step is so small when you look from outside, when you look from afar, it seems to be a single curved line. Okay? Same thing would apply to compression work. If you put the sand one grain at a time, in order to compress the system, it would give these steps to be very small steps, seems to be a curved line. And the blue line and the red line would seem to be overlapping. Okay? That would take place only when the load that you apply is very, very small, one load at a time, and you have to wait very, very long time. Okay, from one equilibrium state to another, you have to wait very long time. All right, if you get that case, it means that compression work and expansion work are the same, and it can be obtained by integration of this curve function. Okay, if you compare between this work, let's say expansion work here should be much higher than expansion work here. In other words, compression work here would be much smaller than compression work here, right? By doing things gradually, one small step at a time, the process seems to be reversible. What does it mean? Let's say I change the mass into a bunch of sand, a small grain of sand, and I put one single grain at a time. Once you put let's say 1 grain in there, or 400 grains already in there, and you put another one in there, the 401, and the first grain of sand you put in there, and you change your mind, you remove that 1 grain out, the system should return to initial state. Okay, so whenever you change your mind and you remove the load instead of putting the load in there, the system returns to the original point. That kind of thing is called reversible process. Okay, the reversible process is basically the process that can be reversed at any point whenever you change the external condition. In this example, the external condition is the mass putting on top of your piston. But in general, it doesn't have to be mass. You can increase the volume. You can make the piston expand by heating it up. Okay, so if you give very small heat, it expand in the small amount. If the external condition in this case would be heat, would apply in very small amount, then whenever you reverse the direction of the heat, the process can be reversed. That kind of process is called reversible process. All right. Most importantly, reversible process occurs only in the system where there's no friction, in frictionless system, which you must learn that in reality there's no such thing as frictionless system. That means the reversible process is somewhat ideal. Okay, we will use reversible process just to calculate the maximum work possible that we can obtain, or the minimum work possible that we have to do. All right. Another important thing for reversible process is that each step must be at equilibrium. So you put a grain of sand in there, you compress the piston for a little bit, you have to wait until the piston reaches equilibrium before you put another grain of sand. If you put the heat, you put very small amount of the heat in there, you have to wait until everything reaches equilibrium before you put another amount of heat. Okay, so the word equilibrium also cover mechanical equilibrium, thermal equilibrium, and chemical equilibrium. All of them must be reached. Then you can retrace the steps backward along the forward path. So it means that if you go from here, from initial state along this path to here, and then you change your mind to go backward, it must go back along the same path. That would be called reversible process. But in real life, all processes are irreversible. Okay, this is very common. The irreversible process would be much more common. The reversible would be ideal. But in general, when we do calculation, mostly we cannot do the calculation of irreversible process directly. So it would be easier to use reversible process as the reference and then calculate the real process based on reversible process. For instance, if we do calculation about an engine, we can say that the engine, if the process, all the processes in the engine are reversible, then let's say the efficiency of the engine will be 100%. For real engine is not reversible, it is irreversible, then we say that of course the efficiency will not be 100%, it will be smaller than 100%. When we do the calculation, we do the 100% case first as the limit. Okay, and then we multiply by some efficiency value and we get what we have for the real process. Alright, so for this lecture, lecture 1B part 2 focuses on the variable work. Okay, two things that I like you to understand from this lecture. First is definition of mechanical work, how we can calculate mechanical work. Basically, for expansion work, we can do it by integration of minus P external dV, and emphasis on the external part. Pressure must be external pressure. Another thing that I like you to get from this lecture would be definition of reversible work, or reversible and irreversible work. Okay. Alright, so this is it for this lecture. Thank you for watching.